High speed GC. In high speed GC, also known as fast, rapid and ultra fast GC, has grown greatly in the course of last few years. High speed GC, which is bound to show important developments in near future, is particularly significant because of its uses in solving environmental problems. One of the primary objectives in developing high speed GC was to provide near real time monitoring for field applications. Because of development in its ease of use, hardware simplicity, ruggedness, size to be reduced and acceptance by emergency response teams, such applications will increase significantly in the next few years. Considering the need for rapid identification of chemicals with a high degree of uncertainty in solutions and situations where an incident has occurred, the use of portable GCMS is certain to grow. As a consequence, a new generation of field portable GCMS instruments, mainly with TOF, that is time of flight analyzer, and laboratory quality performance, is expected to enter the market very soon. High speed GC. The second application for high speed GC relates to one of the most promising recent developments in chromatography, that is GC coupled with GC. In this technique, the effluent from the first column is introduced continuously into a secondary one in the form of a narrow pulses, providing a true orthogonal separation system. The secondary column should be of short, high speed column capable of generating peaks with duration in the 100 to 200 mass range for as long as first column separation proceeds. Until now, GC coupled with GC has scarcely been used for environmental analysis, although it has been shown to be a very suitable technique for the full separation of complex mixtures such as PCBs and surface water contaminants, as well as solving difficult problems such as identification of source of oil seepage. Now, I will try to explain this a little bit, because GC and GC, when they are coupled, the separation that has taken place in one GC is then transferred to another GC. So, now there are wider separations and more number of contaminants can be looked into and can be identified. That is an advantage of high speed GC. Most of the published applications of GC into GC relate to the analysis of petroleum distillates. This can be considered an incentive to the development of commercial instruments and to the improvement of the technique, because the petroleum industry was the first to make extensive use of GCs in the year 1950s and also played a critical role in the development of capillary columns. Now, you would know that in petroleum products, the higher homologue is just CH2 away. That means, if you try to recall the ethane, methane and propane and butane, you see that they are just CH2, CH2, CH2 away from each other, and as we go along the higher homologous series also, they are very narrowly different. That is, only difference takes place between them is the atomic weight difference of CH2, which is 14, and such small differences bring the peaks very close to each other. When the separation is done in one GC, they are partly separated, and then the same effluent is transferred into the second GC and they get separated furthermore. So, that is where the application comes very handy for such petroleum distillates. Latest GC technique, the new generation of fast scanning TOF MS capable of working at high scan rates, that is 500 scans per second, offers the ideal detection technique to couple to GC and GC. So, with this you need to have the time of flight MS analyzer, otherwise it will not solve the situation. So, the adaptation of GC into GC with a TOF analyzer is an ideal situation for such very closely connected compounds. This coupling will provide a powerful technique for the qualitative and quantitative analysis of complex environmental samples, although software programs for automated handling and processing of the tremendous quantity of data generated by these systems will be required. True computer assisted chemical analysis by GC into GC with mass spectral detection appears plausible in the near future. Certainly, this would help in solving the problems of analysis very complex mixtures present in the environment. So, with this we have come to an end of a very important topic, where we had tried to understand the significance of these particular sampling process and high speed GCs. Capillary electrophoresis. This is another very specialized technique which I wanted to draw your attention at. Capillary electrophoresis, or CE, as which we would refer all along, describes a family of techniques used to separate a variety of compounds. These analyses, all driven by an electrical field, are performed in narrow tubes and can result in the rapid separation of many hundreds of different compounds. The versatility and the number of ways that CE can be used means that almost all molecules and even the whole organisms can be separated using the powerful methods. There are a number of different ways of performing CE separations. This makes the technique especially useful as it optimizes for the separation you are interested in, whether this is to be ensuring purity during manufacture or diagnosing illness in a hospital, and many such intricate analysis. Separations driven by electrophoresis also have a novel separating mechanism. This makes them useful in situations where other liquid phases separation techniques are limited or are not practical to be applied. Capillary electrophoresis theory. How does it work? Capillary electrophoresis theory and its background shows that the migration of charged electrical species when dissolved or suspended in an electrolyte through which an electrical current is passed, the cation migrates towards the negatively charged electrode, as you would know, and the anions are attracted towards the positively charged electrode. Neutral solutes are not attracted to either electrodes. Conventionally, electrophoresis has been performed on layers of gel or paper. The traditional electrophoresis equipment offered a low level of automation and long analysis times. However, the detection of the separated bands were performed by post-separation visualization. The analysis times were long, as only relatively low voltages could be applied before excessive heat formation caused loss of separation. So, this was the earlier the infant stage of capillary electrophoresis. However, the advantages of conducting electrophoresis in capillaries was highlighted in the years 1980 by the work by Jorgensen and Leuckart, who popularized the use of capillary electrophoresis. Performing the electrophoretic separation in capillaries was shown to offer the possibility of automated analytical equipment, fast analysis times, and online detection of the separated peaks. Heat generated inside the capillary was effectively dissipated through the walls of the capillary, which allowed high voltages to be used to achieve rapid separations. The capillary was inserted through the optical center of a detector, which allowed on capillary detection. So, you see that one can see the detection while the separation is taking place. Different types of capillary electrophoresis. Capillary electrophoresis has grown to become a collection of a range of separation technique which involves the application of high voltages across buffer filled capillaries to achieve separations. The variations include separation based on size and charge differences between analytes, capillary zone electrophoresis, that is CZE, or free solution, that is CE. Separation of neutral compounds using surfactant micelles, micellar electrokinetic capillary chromatography, or sometimes referred to as MEKC, sieving of solutes through the gel network, that is capillary gel electrophoresis, and separation of zwitter ionic solutes within a pH gradient, which is called capillary isoelectric focusing. Capillary electrochromatography is an associated electrokinetic separation technique which involves applying voltages across the capillary filled with silica gel stationary phases. Separation selectivity in CEC is a combination of both electrophoretic and chromatographic processes. Many of the capillary electrophoresis separation techniques rely on the presence of an electrically induced flow of solutions, that is electroosmotic flow, within the capillary to pump the solutes towards the detector. So, how the process takes place, how there are different different types of capillary electrophoresis activity taking place gives an idea that what a huge range it is all by itself, almost like equivalent to a GC or an HPLC. And in the modern times, capillary electrophoresis is rarely being used largely by analysts. Advantages of capillary electrophoresis: has very high efficiency, meaning hundreds of components can be separated at the same time, requires minute amounts of samples, is easily automated, can be used quantitatively, and consumes limited amounts of reagents. So, you see, in all aspects it is one of the most efficient and economical method. Capillary electrophoresis, if one has to see it in pictorial way, I have taken this example and would retain it for some time, so that one can see how these charged ions are first separated and how they are transferred one by one to the different electrodes, and they are trapped there, and there is a recorder which gives the recording to show how they are analyzed simultaneously. Basics: the capillary electrophoresis uses a high voltage to obtain separation of components, can be an orthogonal technique to HPLC. That means, it can be in competition with the HPLC machine, better plate efficiency than HPLC possible, and shorter run times. So, you see it has an edge over the HPLC because it requires only very small time to run and do the analysis. Uses a silica capillary filled with buffer. Analytes are injected onto one end, voltage is applied, separation occurs, and it is detected either by a UV or a conducting device or a mass detector. Capillary zone electrophoresis. Capillary zone electrophoresis, that is CZE, is one of the widely used type of capillary electrophoresis because of its simplicity and versatility. As long as a molecule is charged, it can be separated by CZE. That means, for capillary zone electrophoresis, the molecule must have some kind of charge, otherwise neutral molecules cannot be separated. This makes the application of CZE very diverse, being used for peptide ion and enantiomer analysis. CZE is also the easiest form of capillary electrophoresis to perform, because the capillary is only filled with buffer. Separation occurs as solutes migrate at different velocities through the capillary. Another advantage of CZE is that it separates anion and cations in the same run, as what we saw in the picture which was shown earlier. Sometimes, and some things that some of the other modes of CE cannot do it. This dual separation is due to the electric charges that are present, which help the migration of some analytes while hindering the migration of the others. However, CZE cannot separate neutral molecules, which I have told time and again. There are only simple swept through the capillary and elute with the help of this electroosmotic pressure. Buffer selection, that because everything is happening in this buffer solution. So, the selection of the buffer solution is very crucial. The buffer is absolutely vital to a capillary electrophoresis separation. The buffer affects both the electroosmotic pressure and the analytes with factors such as pH and concentration, all being very important. A buffer for use in CE should possess the following properties. It should be a good buffering capacity in the pH range of choice, low absorbance at the wavelengths of detection, low mobility, that is large minimum charged ions to minimize current generation. Biological buffers such as tris and borate are especially useful, as they are generally large and so can be used in high concentrations without generating too much current. A disadvantage of these is they have often strong UV absorbances. So, now I said it should not have an absorbance in the region where the analyte is present. So, but some of these buffers are very strong UV absorbers. So, that is a little tricky. One needs to choose the UV the buffer solution which does not interfere with the UV activity of the analyte. There are chiral selectors, and chiral analysis is becoming increasingly important in the food and drug industries. Currently, chiral analysis are performed by GC or HPLC, but now the capillary zone electrophoresis is picking up. Cyclodextrins are most widely used chiral selectors. CDs are non-ionic cyclic oligosaccharides consisting of 6, 7 or 8 glucose units. A little while ago I had shown you what cyclodextrin looks like. CDs have the shapes of a hollow truncated cone and a cavity diameter determined by the number of the glucose unit. The cavity is relatively hydrophobic while the external surface is hydrophilic. So, the cyclodextrin molecule has an exterior which is hydrophobic, it has an interior which is hydrophobic and has an exterior which is hydrophilic. The circumference contains chiral secondary hydroxyl groups. Chiral selectivity results from inclusion of a hydrophobic portion of the solute in the cavity and also from hydrogen bonding in the chiral hydroxyl groups. So, that is how the chirally it is selected. Now, if you see the 3D picture of cyclodextrin, it will be much more clear to you that how it forms a circumference and the inner diameter is hydrophobic and the outer diameter is hydrophilic. Gel electrophoresis. Gel electrophoresis is usually used in biological system to separate proteins and nucleic acid. It separates molecule as they move through a polymeric network which is present as a molecular sieve. As the solute migrates through the sieve, it becomes hindered, with large molecules more hindered than small ones. Capillary gel electrophoresis is similar to slab gel electrophoresis. Using capillary has a number of advantages of slabs of the gel. Gel tend to build up a lot of heat which is detrimental to the separation, whereas capillaries are much better at dissipating this energy. Therefore, one can use fields many hundreds of times larger without too much joule heating. This leads to a large increase in the overall resolution of the separation. and that is how also the use of capillaries allow the use of detectors and automate the process, making it a quantitative and reproducible method. Polyacrylamide and agarose have traditionally been used as gel matrix in slab separations. Polyacrylamide has small mesh spacing, making it more suitable for separating proteins, whereas agarose has very large pores, making it more suitable for DNA. The gel used in capillary electrophoresis often are present as a solid piece, but instead occur as many separate strands. While using a slab, a solid polymer is necessary in order that the gel can be handled and analyzed. This is not necessary in the CGE method, as the capillary provides a support for the separation. This means that liquid polymers can also be used. This is advantageous as it allows the matrix to be replaced between runs, reducing cross contamination. So, one can keep on changing the gel as and when required, when it is felt that the gel is contaminated, and gel electrophoresis is nothing but a kind of a mesh through which some can pass and others will be restricted. So, for polymer matrix for CGE, the applications are that polymer application cross-linked dipolymers are used, and for polyacrylamide oligonucleotides, DNA and so on can be used. So, here is a kind of a compatibility, what can be used for what kind of molecules. Capillary electrophoresis has a wide range of application in drug substance, drug products, raw material identification, vitamin identification, analysis of DNA fragments, antibodies and many other biological analysis, and the list is exhaustive. So, with this we have come to an end of the capillary electrophoresis, which is such an important area for the nucleic acid and the protein analysis.